Okay, guys, in this section, we're going to talk about integration of rational functions using partial fractions. We're going to look at four cases here, but before we jump in, let's talk about where this kind of comes from. Every improper rational function can be expressed as the sum of a polynomial function and a proper rational function by using long division. So we're only going to look at how to integrate proper rational functions. So to do this, you first need to write it as a sum of simpler functions. These are called partial fractions. So for example, if I have the sum of 2 over x minus 1 plus 3 over x plus 4, if you get a common denominator and add those together, this would actually simplify to 5x plus 5 over x minus 1 times x plus 4. And that would be 5x plus 5 over x squared plus 3x minus 4. So if you were given the integral 5x plus 5 over x squared plus 3x minus 4, and you knew how to get it into this form right here, then you could rewrite the integral as 2 over x minus 1 plus 3 over x plus 4. And then those are just natural logs. Natural log absolute value x minus 1 plus 3 natural log absolute value x plus 4 plus c. Now, the tricky part is typically the integrand is going to be expressed as a rational function, and it's relatively easy to factor the denominator. The thing is to get them as a sum of simpler functions called partial fractions. This technique is called partial fraction decomposition. It involves a bit of algebra, especially when we get to the more complicated situations. In this first case, we're going to look at a rational function whose denominator contains only distinct linear factors. We'll call that case 1. So if we want to find the integral of x over x squared minus 5x plus 6, you can try u substitution or try the log rule, but it's not going to work in this case. The first thing we want to do is begin with factoring the denominator. So you would have x over x minus 3 times x minus 2. Just take the integrand. What we're going to do is we're going to set up the partial fraction decomposition. Anytime you have linear factors, the numerator is going to be a constant. So we set it up like this: a over x minus 3 plus b over x minus 2. And then what we do is we clear the fractions by multiplying both sides by the common denominator of x minus 2, x minus 3. So when I distribute it here, a factor of x minus 2 cancels and you get b times x minus 3. When I distribute it here, the factor of x minus 3 cancels and you get a times x minus 2. When I distribute the common denominator to the original integrand, divides or cancels the x minus 3 and the x minus 2, and you just get x. So basically all we're doing is clearing the fractions there. The next step is you're going to want to pick strategic values of x to eliminate one or more of the factors to be able to solve for either a or b. So for example, if I let x equal 2, then this would be 2 equals a times 2 minus 2 would just end up being 0. And then you would have b times negative 1. So b times negative 1 equals 2 implies that b equals negative 2. Another strategic value would be to cancel the term that involves b, and that's going to be if we use x equals 3. So we take this original equation with 3 plugged in. So 3 equals a times 1, and then the b term would go away, and that would be a equals 3. So we know our constants of a and b, and then what we can do is write the integral as 3 over x minus 3 minus 2 over x minus 2 dx. Now, a word of caution here. I know that the constants in both of these factors are 3 and 2, and we ended up with a 3 and 2 here. That's not always going to be the case, so don't mistakenly think there's a pattern developing there. And then the antiderivative is going to be 3 natural log absolute value x minus 3 minus 2 natural log absolute value x minus 2 plus c. We can further simplify this by the power rule and for logs by taking the 3 and writing it as the exponent here and the 2 as the exponent here. And then since you're subtracting logs, you can rewrite it as a quotient. So it'd be log absolute value x minus 3 cubed over x minus 2 squared, all of that plus c. This line here is sufficient, but just wanted to show you some simplification here. Okay, so the next example we want to look at is a definite integral. So we'll do the same thing in this case. First, start by factoring the denominator. So this is going to be 4x minus 1 over x minus 4 times x plus 1. We'll set up our partial fraction decomposition. A over x minus 4 plus b over x plus 1. Then if we multiply by the common denominator of x minus 4 times x plus 1, you would have 4x minus 1 equals a times x plus 1. Be careful, because when you multiply by the common denominator, this x minus 4 is going to cancel. And then the b term would have b times x minus 4. Again, picking strategic values, x equals -1. This would be -5 equals, this is going to go to 0, and this would be -5b. So b is equal to 1. The other strategic value we're going to pick is 4. And so 4 times 4 is 16 minus 1 is 15 equals a times 5. The b term is canceled, so a equals 3. Now we can set up our integral, and then we take the antiderivative of each one. You would have 3 natural log absolute value x minus 4 plus natural log absolute value x plus 1. This is where we would then substitute the values of 5 and 7 in. You can actually simplify this to natural log of x minus 4 cubed times x plus 1, and then plug in the 7 and the 5. So you would have natural log of, if you plug 7 in, 7 minus 4 is 3. 3 cubed is 27 times 7 plus 1 is 8 minus the function evaluated at the lower limit. If you plug in 5, 5 minus 4 is 1. 1 cubed is 1. And then 5 plus 1 is 6. So you would have natural log of 27 times 8 over 6. The 8 and 6 can cross cancel to a 4 and a 3, and the 27 and 3 can cancel to a 9. So this simplifies to natural log of just 36. Next thing we want to do is look at what happens if you have repeated linear factors. This is what we would call case 2. Here, we set it up in a similar way, but you have to account for all the repetitions of each linear factor. So you would have 1 over x times x minus 1 squared equals, so that's the integrand, a over x plus b over x minus 1 plus c over x minus 1 squared. If that was x minus 1 cubed, you would have to have plus d over x minus 1 cubed. Okay, so that just that little tidbit there, whenever you have repeated linear factors, you have to account for each factor. Cross multiplying by the common denominator, you would get 1 equals a times x minus 1 squared plus b times x minus 1 plus c times just x. Picking strategic values, x equals 0, you would have 1 equals a plus 0b plus 0c. So a equals 1. If you pick x equals 1, the a term and the b term are going to go away. So you'd have 1 equals c times 1. So c equals 1. Now there's no other strategic values, but what you can do is use the values of a and c and pick another x value. So like let's pick x equals 2. That would mean that 1 equals a, which is 1, times plugging in 2 to the x minus 1 squared would just give you 1, plus b, which we don't know yet, times the x value we're using, which is 2 times 2 minus 1. It's 1, plus c, which we know is 1, times the x value we're using, which is 2. So you have 1 equals 1 plus 2b plus 2. So you would have, you subtract 1, subtract the 2, you'd have negative 2 equals 2b. So b equals negative 1. And then we can get our integral. Now this is going to anti-differentiate to natural log absolute value of x minus natural log absolute value x minus 1. And be careful with this last term here. This is similar to 1 over x squared. You could use u equals x minus 1. And what you would get is negative 1 over x minus 1 plus c. And there you have it. Okay, we're going to do one more example of a case 2 situation. And here we have the integral of 3x squared plus 49 all over x times x plus 7 squared. So sometimes these can get a little bit complicated. So just make sure that you're using a lot of organization with these. So 3x squared. So we would have a over x plus b over x plus 7 plus c over x plus 7 squared. Then multiplying by the common denominator, you'd have 3x squared plus 49 equals a times x plus 7 squared plus b times x plus 7 plus c times x. Strategic value would be x equals negative 7. Negative 7 squared is 49 times 3 plus 49 is going to give you 196 equals the a and the b are going to cancel negative 7c. Dividing by negative 7, you would get c equals negative 28. If you pick x equals 0, then you would have 49 equals 49a, and the b and c terms would cancel, which means that a is going to equal 1. There are no other simple strategic values, but if I pick x equals 1, it's simple to plug in. You would have 3 times 1 squared plus 49, which is 52, equals 1 plus 7 squared would be 64a. And then you would have plus 8b plus c. I already know that a is 1 and c is 28, so this would become 52 equals 64 plus 8b minus 28. If you solve that down, you would get b equals 2. So now we have our integral. Anti-differentiating, we have natural log absolute value of x plus 2 natural log absolute value x plus 7. And then this is, again, another form that's like 1 over u squared, the last one, where u is equal to x plus 7, and the du would line up pretty much, and you would just have a negative, or you'd have a 28 there. But remember, when you anti-differentiate the 1 over u squared, you're going to end up with another factor of a negative. And since the 28 over x plus 7 is being subtracted, you'll end up having plus 28 over x plus 7 plus c. There you have it. All right, guys, that's it for this one. Hope that was helpful to you. And we got one more video where we're going to get into case 3 and 4.